Welcome back again. In this lecture, we're going to be looking at deflection, how things can fail by deflection, and thus how we're going to avoid them failing by deflection, and how we look back at some mechanics and materials to look at the diagrams, specifically the shear and bending moment diagrams, and how they're going to be useful for us within the machine element design context. All right, so let's begin as we've discussed this introduction of failure by deflection by discussing what do we mean by failure. So let me go ahead and define failure here. So failure is a loss of functional performance. So a loss of functional performance means that what it was able to do before it's no longer able to do. So this makes sense with when a material breaks or when it cracks, but it's certainly possible within the context of how a product is being used that it can deflect or change shape in such a way that while it's not technically broken, it's of no good use. So imagine for a moment having a floor that can deflect, can bounce a good foot when you walk on it. No one would consider this floor to be a good floor if it bent that much. And it didn't matter that the floor didn't technically break. We would consider it a failure as in a loss of functional performance. So, as I said, the ways that we can get there is a high amount of stress, which can lead to failure. So this is the stress that is above or beyond the yield strength of the material. But we can also have a stress that causes deflection below that yield strength, which exhibits elastic deflection that is unsatisfactory. So recall a diagram called the stress-strain curve. And every material has its own stress-strain curve. So when we put some normal stress, this is like the Instrom machine test, we put some normal stress on this part, it experiences some amount of strain. So steel and aluminum tend to have this straight horizontal part, the straight part, up to a point where it starts to behave slightly differently and then eventually breaks. So this looks more like steel. So there is this area where as you add more stress to the part, the strain changes with the stress in a linear fashion. This is when the material obeys Hooke's law, and strain is proportional to stress by the modulus of elasticity. That is, the slope of this line is the modulus of elasticity. And the point where that is no longer true is called the yield strength. So it might be called sigma yield, or it might also be called yield strength with the SY. There's another point, the highest point stress that you can put this material under, which is called the ultimate strength. And this will be the ultimate strength in tension. Strength, ultimate tension, SUT. Within Hooke's law region, that is this area right here, is considered the elastic region. Everything below the yield point is elastic. Deformation. If you cause any sort of deformation, it will go back to its original shape. After the yield strength, we have plastic deformation. So this should all be reviewed for mechanics and material. But what's important to us is that we obviously know that a part fails once it hits its plastic yield strength. And we'll talk about static failure theories, which lead us to find what, under certain stress scenarios, what that point is. But before we get there, we should consider what happens if it fails within the elastic region. And there's two ways it can fail within the elastic region. It can either fail over time due to cyclic loading. That's the fatigue loading we'll look at towards the end of this first part of this course. And before that, it may deflect in such a way that it's bent too much to perform the operation that we want it to do. So in order to know whether it's going to fail, we actually have to know something about the system. What we'll need to know is called the operational envelope. The operation envelope is the amount of space that we allow our product to move within. So this often shows up in tolerances. And it also shows up in the amount of extra margins that we add to our operating environment. All right, so let's discuss now about how things actually deflect. Because every part of a product put under any amount of stress will deflect. Now that deflection may be a very tiny amount, but it will deflect. So when we talk about deflection, we need to consider the loading that it's under. So let's start with direct axial. And again, we consider direct axial and direct shear basically to be two different views of the same area. So recall the equation for deflection is delta force times length of the part over the modulus of elasticity times the area. So that might just be an equation you memorized. And this is when we're talking about we put some load F equal and opposite on both sides. It has some length L and some cross-sectional area A that force acts against, and it's made of a material with a modulus of elasticity E. That's about the most simple view of deflection we can get. So I'd like to take a moment to think about what this equation actually looks like. So hopefully from physics you remember that a spring, or a resistor it kind of looks like, but a spring has a relationship with deflection that is constant. So the force you put on a spring causes some amount of deflection in a constant linear relationship, as long as we're in the working range of that spring. So we'll get some more into spring design, but I'd like to consider for a moment that everything is in fact a spring. So if we took the same deflection equation and put the force on this side, all of a sudden we've got deflection, that was our x before, and within here we've got the parameters which affect how springy our material is. Obviously the modulus of elasticity, the cross-sectional area, and the length, the geometry of the part. So there's geometry and material properties. When we talk about deflection, you must know the material properties. So when we talk about stress, what the thing is made out of is inconsequential. We don't care. But when we talk about deflection, you must know what the material is made out of, unless we can figure out deflection from both ends. All right, so that's direct axial. Now it also is possible that just the environment that a product is under can cause it to deflect, and that's often referred to as the deflection due to temperature. And it is related to some material property alpha, the absolute change in temperature, and the length of the part that we're talking about. So this says that this will change some delta temp based on the temperature, the absolute temperature change that the part goes under. And this can be multi-directional. You can build some pretty complicated ones. We won't be looking too much at temperature changes within this class. All right, so that's direct axial loading. We can also look at torsional loading. In torsional loading, what we find, remember that's the twisting. So when we put some torque, T, over a part with a length L, it has some material property G, the modulus of rigidity, and this cross-sectional area has a moment of inertia about the twist axis, so therefore it's a polar moment of inertia, J. So all those things together, we get the twist angle in radians, don't forget, is related to the torque, and in the same fashion, we're going to have geometry, length, and J, and material properties, G. TL over GJ. All right, let me put over here all of our bending deflection issues. So we usually, when we describe how things bend, we actually begin the introduction by talking about deflection first and working out the integrals from there. So let's call the deflection of a bent beam V. The slope of the beam would of course be the derivative with respect to the length. So that is the slope of that beam is the first derivative, so dv dx. That is the slope. We can take the derivative again, and what we end up with is the bending moment. But now, to transfer between deflection and stress, we're going to need to know material properties and geometry again. So that's where the E and the I, the moment of inertia and the modulus of elasticity, come from. We have the second derivative of deflection with respect to the length as we go across the length of the beam and bending. And we can take the derivative again, of course, and come up with the shear force diagram, or the shear force acting throughout the part. So that's now the third derivative along the length. And finally, we can come back to the loading that's actually the part is under with the final fourth derivative. So usually, we in this class and in most situations, we know the loading and we are interested in finding the deflection. So we're going to come back to this when we talk about shear and bending moment diagrams. But before we get there, I'd like to talk just one little bit about how we can deal with the fact that in most situations we have lots of areas for something to deflect. So deflection is additive. And this is great news for us. It means that we can find and break things into parts and then add all of the little deflections together. So we can take something, assume it's like a miniature version of it, and add it all together. So there'll be a problem within the textbook that you guys will work out as a practice problem that looks something like this. There is a beam sticking out of the wall, kind of represents if we had a torque wrench spinning on a stuck bolt. We can put some force P here, and the question is, it's obviously going to spin around a little bit as this material changes. How much is this actually going to change? So within our operating environment, if this was a type of thing where we needed to build an enclosure around here, we want to make sure that in the normal play of this thing, it's not going to interact with the environment in a way which causes some functional loss. So if we took this thing into parts, let me leave some labeling here, A, B, and C. We can add up the little bits together. So first of all, we can realize that if we had a wall at B, we'd have this situation. And that's going to add up to a little bit of deflection. Let's call that deflection 1. Then we can consider the portion between A and B. So between A and B, that looks like two things. That looks like a little bit of this from when we translate P over. So we get a little bit of deflection. And because the load is eccentric, it's also going to cause some amount of twist. I drew that backwards, it should actually go the other way. So that's going to result in some twist angle in radians. We can multiply that times the length that is between B and C and come up with how much it's going to deflect between that part. So total deflection is going to be the sum of all the little parts. Now let's consider another way that a part can fail below our yield strength and below the point where it would start to crack, but it may in fact buckle under certain scenarios. So if we have any component that is experiencing axial stress, it is worth our time to consider, is this part going to buckle? So oftentimes shafts carrying gears will be under some axial force if they're helical gears or torsion gears, which are putting pressure on that shaft itself. Generally, this force is so small we're way, way below buckling, but it's always important to check. So of course, the stress due to the force acting over the cross-sectional area of our part is normal stress equals P over A. So there is some critical stress, which is way, way below the yield strength usually, where a part under an axial load can buckle. So we need to figure out our buckling criterion. And thankfully, our good friend Euler is here to help. So Euler developed the force P critical necessary to get a beam to buckle is related by pi squared times the modulus of elasticity. Again, we're talking about deflection, aren't we? So we expect to see geometry and material property over the length squared times a factor of k squared. And there's a couple different formulations for this. But the way I'm using it is k, where k depends on how we actually fix this thing. So the equation straight over, the first way Euler looked at this situation was both ends pinned. The next way you might be able to want to look at it is if one of the ends is fixed and one end is pinned. So what do these things mean? Well, fixed means that it can't rotate about its end, and pinned means that it can. The movement side to side and up and down is fixed when it's pinned and when it's fixed. The best case scenario is when it's fixed on both ends. And the worst case scenario is when it's fixed at one end and free at the other. So we can develop a P that is n times smaller than the P critical. So if we have P critical equals n times our P actual, then this n becomes our factor of safety for buckling. So we might want to call it buckle. Our factor of safety against buckling. And throughout this course, we'll use the lowercase n as a factor of safety for the most part. All right, I mentioned before that we were going to get back to shear and bending moments. So recall when we had a beam under bending, we did what's called shear and bending moment diagrams in mechanics and material. So let's draw our pretend beam here. And not that you would ever actually see this, or that we'll be dealing with a lot of beams in this class, but what you'll find is a lot of things act like beams. So we're usually given some sort of beam. It's under some load, maybe P. We can even make this load somewhat complicated. And some distributed load. Well, what we need to do first of all is statics to figure out, say, at A and B here, what are our reactions? And what we're going to find out is that they're in proportion to where the loads are acting and the magnitude of those loads. And since there's nothing in the y direction, I'll just keep with AY and BY. We'll assume they're up here. Probably a pretty good assumption. And some force acting down P and some force W. Distributed force W. So this would be force per length. pounds per inch, for example. Now, of course, you don't have to draw it like a beam anymore, but I find it helpful to remember what we're talking about. So our diagrams that we could develop with the shear diagram, V, this is the shear force throughout the part. There's lots of ways to doing this. My favorite way is to pretend I am the beam and I'm feeling these things. This is sort of a Zen approach. So the first thing that happens to me is I get pushed up by this AY, and I get pushed up how much? Well, by the magnitude of AY. And then nothing happens to me, and all of a sudden I get to this point, and I get pushed down by a magnitude from AY by a magnitude down of that first P load. And then nothing happens to me for a while, and all of a sudden I'm slowly getting pushed down more and more by this W per L length. Let me bring it down here. And we can figure out how much it goes down based on W times L from how far we got down, pushed down by that original P. So this is just a process of accounting. And then nothing happens to me, and then finally I should get pushed back up exactly by a magnitude of By. Now, if something went wrong here and you ended up here, you know that's wrong. So you'll always begin and end at the zero. So now we can think about the bending moment diagram. So the bending moment diagram is the integral of the shear diagram. And we can sit there and do the calculus if we want, or we can just remember the integrals is the same thing as saying the area under the curve. So the area under this curve grows to a point, and then it starts to decrease statically to a point. And then we get some interesting behavior when we have distributed loads. So this might not be a perfectly accurate bending moment diagram, but it gets the point across. And what you'll find out is your bending moment diagram doesn't need to have every single part exactly right. What we really need to know about is where the stresses are maximum. So here we've got our maximum shear, and here is where we're going to find our maximum bending moment. So we can look across our diagram, find the absolute maximum shear force that it's under. It might be over a large area and be constant. And that maximum shear is where we're going to calculate our transverse shear and see if that's super high right where that is. Remember that a part doesn't experience transverse shear and maximum normal stress in the same spot. They experience them one at the neutral axis and one as far as you can get away from the neutral axis. So from the bending moment diagram, we're going to want to find what is the max bending moment. And from that, determine our maximum normal stress as my I. The bending moment times the distance from that neutral axis divided by the moment of inertia. All right, so this tells us the stresses, which will be important from our last video when we talked about finding the principal stress values for a particular location. But what it doesn't tell us is how much this thing deflects. For that, we would have needed to do calculus or the integral or start it backwards. So I suggest two ways of finding deflection for beams. The two ways are the easy way. That is, when the situation is just one or two loads, you can break it up very easily and use superposition. Superposition, of course, is when you look at the diagrams in the back of the textbook or in some other helpful diagram document that you have, or look it up on Google, and you can find out, okay, the deflection from this type of loading, where we've got some load in the middle, can be added to the deflection from a distributed load. And we can come up with what the total deflection is, assuming each one of those independently. That's the easier way. The more complicated way, but as soon as you have more than a few forces, it becomes the easy way. So I say the easy way, meaning when there's just one or two things happening to that beam, it's probably easier to use superposition. The more complicated way, or when there are more forces acting on it, so if we've got a gear system with multiple gears acting on this beam, on the shaft, which is effectively a beam, supported in bearings, which are the support beams, that pins at the end, then what we will be concerned about is finding deflection. We'll want to use, there's multiple methods here, but I tend to enjoy using singularity functions. So if you haven't used that method before, or if it's new to you, you can check out the textbook, and that will be a helpful skill for you to be able to have. So if it's easy, use superposition. If it's a more complex loading scenario, I would suggest using singularity functions or calculus, or one of the other Castigliano methods, or one of the other methods that you may have learned. Well, that'll do it for this video. Until next time.